In this video on extreme values and mean value theorem, we're going to pick up with the mean value theorem. So if you have a function that is continuous and differentiable between points a f of a and b f of b, then the slope of the secant going through those points is just this. This should look familiar. This is just the change in y over the change in x. This is just your slope formula. And the key is we are continuous and differentiable. Now, occasionally, they'll just say differentiable. Differentiability implies continuity. So sometimes they won't say that it's continuous. Now, the mean value theorem, it says if a function f of x is continuous at every point on a closed interval from a to b, and differentiable, differentiable at every point of its interior from a to b, then there's at least one point c at which f of b minus f of a over b minus a, this is just the change in y over the change in x, is equal to f prime of c, which is your instantaneous rate of change. So we're saying that the instantaneous rate of change is equal to the average rate of change. So this is my instantaneous rate of change is equal to my average rate of change, which is just my slope formula. Okay, so here is what we're looking at graphically. My slope of my secant line is equal to the slope of the tangent line. Remember your tangent line? This is your instantaneous rate of change, and this is your average rate of change. At some point C, between the A and the B, this slope is going to equal this slope. And that's what we're saying. This is what the mean value theorem says. All right, so here's a sample free response question using mean value theorem. It says the functions f and g are differentiable for all real numbers and g is strictly increasing. Okay. The table gives values of the functions and their first derivatives at selected values of x. The function h is given by this. H of x is f of g of x minus 6. Explain why there must be a value r between 1 and 3 such that h of r is equal to negative 5. Do you remember a theorem from Unit 1? Well, hopefully you remember something called the intermediate value theorem. And that's what we're looking at here. Now, the difference in these two equations, it says explain why there must be a value c between 1 and 3 such that the instantaneous rate of change is equal to negative 5. This is our mean value theorem. And so let's just work through both of these. Okay, so first thing, we need to find our coordinates. So part A. Let's see, what is f of 1? Oops, not f, using the wrong. Let's try h. H of 1. If we plug it into this function, this f of g of x minus 6, this is going to give me f of g of 1 minus 6. G of 1, if I look on the table up here, g evaluated at an x value of 1 is equal to 2. So f of 2 is equal to 9. So I'll write it myself. So my steps. So g of 1 we said was 2. F of 2 from the table gives me 9. 9 minus 6 is 3. So I've got the coordinate 1, 3. Now let's evaluate the other endpoint, 3. F of g of 3 minus 6. And so g of 3 on the table is 4. F of 4 is negative 1. So we have g of 3 we said was 4. F of 4 is negative 1. Negative 1 minus 6 is negative 7. So 3, negative 7. If it says it's differentiable, then we know this is a continuous function. So if I just want to look at, see what this looks like. If I had the points 1, 3, and 3, negative 7. So 1, 3, and 3, negative 7. I don't know how it wiggles, but it's going to connect these 2 points. That means, and if it's differentiable, it's continuous. That means every y value is going to be accounted for between a y value of 3 and a y value of -7. All right, and h of r, of course, is your y value. So we're looking, is there a y value of -5? Absolutely. It is captured between 3 and -7. So we can say, let's see, by the intermediate value theorem, let me see if I can write this. H of 3 is less than -5 is less than h of 1. There exists an r value such that, let's see, h of r is equal to -5. And then also, just one more thing, we need to add in that this, because this is a continuous function by the intermediate value theorem, the y value is captured between these 2 y values. That means there is a corresponding r value that is, I'm sorry, well, let me see if I can see that. I need to say an r between, such that r is, oh man, I messed this up. R is between, I don't know, let's see if I can fix this. An r between 1 and 3. That's fine. It's fine. Well, we can work on the grammatically fixing that later. Okay, let's take a look at the mean value theorem though. So let's find the slope of the secant line. So for part B, if I find the slope of the secant line, h of 3 minus h of 1 over 3 minus 1. And this is h of 3, what was that, -7 minus 3 over 2. So that's -10 over 2, which is -5. Okay, so the slope of the secant line is -5. So there must be a derivative between 1 and 3 by the mean value theorem. So the mean value theorem says that the slope of the secant line is equal to the instantaneous rate of change. And since this is a differentiable function, we know it's continuous. So let's see, I think I've got the answer over here. Yeah, I kind of butchered that justification. So let's take a look at how they worked it. They evaluated h of 1 and h of 3. That's what we did. And we said that it was captured between, -5 is between h of 3 and h of 1, and h is continuous. I told you needed to write that. By the IVT, there exists an r between 1 and 3. Okay, so I pretty much said that, just not as pretty as it's written here. And so there's where you get your points. In part B, here is the slope of the secant line, and we figured it is -5. Since h is continuous and differentiable, by the mean value theorem, there exists a value c. And I didn't write this, but this is what we need to write. There exists a c between 1 and 3 such that the instantaneous rate of change at c is -5. Awesome. Okay, so here's another example. It says the graph of a differentiable function is shown above on this closed interval from -4 to 3. How many values of x in the open interval satisfy the conclusion of the mean value theorem? Okay, so we know it's at least 1 because that's what the mean value theorem says. Are there more? Okay, so what we're looking for, it says the slope of the secant line would have to have the same slope of a tangent line. So how many tangent lines can we draw that are going to have the same slope as this guy? Here's my secant line on this interval. Okay, well, let me show you. I can draw a tangent line right here that has the same slope. I can also draw a tangent line right here. Whoops, that's kind of wiggly, but right here where I have the same slope. And additionally, I can draw a tangent line right here that would have the same slope. So in this case, I've got 3. I've got 3. All right, let's take a look at one more example. And this is a good one. Okay, so we have a function is f is continuous. Function f is continuous on this domain from -2 to 4. F of -2 is 5. So when I see points, I'm going to start to graph. So let's see. I have f of -2 is 5. Because I'm a visual learner, and it certainly helps when I can plot some points. F of 4 is 1. And f prime and f double prime have the following properties as on this table. So find where all absolute extrema of f occur. Okay, so we know it's continuous. And let's see, absolute extrema, those are going to occur at our critical values or our endpoint. So this is, we're looking at like our candidates test. So let's see if we can sketch what this graph would look like. Okay, so I've got a couple of points so far. What I do know is from -2 to 0, I'm increasing. My slope is increasing. Now, f double prime gives us concavity. So if it's positive, it's concave up. So I know between -2 and 0, I'm increasing and I'm concave up. So I'm going to look something like between -2 and 0, I'm increasing and concave up. And then at 0 does not exist. Well, since it's continuous, I know that can't be like an asymptote, but I'm guessing that's either a corner or a cusp. So it's either going to be doing something like this, or it's doing something like this. So let's continue to investigate. All right, so next piece of information we've got is that between 0 and 2, I'm decreasing. My slope is decreasing, but I'm also concave up. So if you can imagine what decreasing and concave up between 0 and 2. So I'm decreasing and concave up. So it's like a little cusp right there. And then at 2, I've got a horizontal tangent. So it's going to do one of those cubic things, is what I'm guessing. So I'm concave up, and then I go 0. And then what do I have over here between 2 and 4? I'm decreasing and concave down. So it's looking something like this. A little strange. All right, so find where all the absolute extrema of f occur. Well, they occur where the derivative is equal to 0 or where it's undefined. And so I can say that at x equals 0. Whoops. And the absolute extrema would be your max and minimum. And so my absolute extrema occur at x equals 0. Now I don't know what that corresponding y value is, just because I don't have any more information. So all I know is at x equals 0, and that is where my derivative does not exist. Find where all the points of inflection occur. Points of inflection occur where your concavity changes. So if I'm looking on my chart, I go from a positive to a negative concavity. Right here at this x value of 2 is where I have a point of inflection. And so at x equals 2, and that is because f double prime of x changes from positive to negative. And then sketch a possible graph, and we are done with that. Okay, I think we are done with our notes on mean value theorem, and it is now time to practice.